So, welcome to Module 6. Now, Module 6 is going to reuse resources that we've already hit on. So, we've seen our Arduino discussed in multiple chapters along the way. In Chapter 4, we saw it relative to Wi-Fi. Now, the things that we can do in Chapter 5 have focused on Raspberry Pi. Much of that we can do with Arduino. Okay, so I don't have a specific chapter dedicated, one chapter dedicated to Arduino, but where we'll start off with is here in Chapter 4. So most of what I'm going to walk through is sprinkled a little bit here and there. It could be some of the stuff over here on Wokwi. So let's start out. Like I said, our focus is going to be on the Arduino platform, and it's a foundational tool in the world of IoT prototyping and embedded system development. So whether you're building a smart home device, much like what we talked about in Raspberry Pi, and we're talking about wearable health trackers or industrial sensor controller, Arduino gives you building blocks to bring your IoT devices to life. So in this lecture, it's going to help you understand how Arduino works, how it fits into the IoT landscape, and how to use it effectively to build and simulate real-world systems. We'll also explore some common communication protocols, interfacing methods, and examples of practical applications, all of which can help prepare you for the mini project paper you'll be writing at the end of this module. So let's start with what Arduino actually is. So Arduino is an open source electronics platform based on easy to use hardware and software. The core of Arduino is a microcontroller, like the Atmega 328P. And that's in the Arduino Uno. And we see that here, an example of it in Wokwi. That can be programmed using the Arduino IDE, Integrated Development Environment, with simplified C or C++ code. So Raspberry Pi, we used Python. Arduino, we use C or C++. It's designed for anyone, from hobbyists to engineers, to prototype and deploy interactive hardware-based systems. In the context of IoT, Arduino serves as the perception layer of the architecture. It's the device that interfaces with the physical environment. Whether it's sensing temperature, motion, light, or sound, or actuating motors, LEDs, or relays, Arduino is responsible for turning analog world inputs into digital information that can be processed or transmitted. One of the advantages of Arduino is its modularity. There are countless sensors, shields, and modules available that you can connect directly to an Arduino board. These include temperature sensors like the LM35, the DHT11, gas sensors like the MQ series, and wireless communication modules like ESP8266 or an NRF22L01. You can use jumper wires and breadboards to quickly build and test prototypes. And you can scale up with custom PCB designs when needed. So the Arduino also shines in terms of affordability and simplicity. Boards like the Arduino Uno or the Nano are inexpensive and they're widely available. The community is vast, meaning there's a wealth of open source libraries, code examples, and documentation to help troubleshoot or enhance your projects. Now let's walk through how an Arduino powered IoT system might work. So imagine you're building a smart irrigation controller. You'd use soil moisture sensors to collect data about the hydration level in different parts of a garden. The Arduino reads the data through its analog input pins. It applies logic to determine whether the soil is too dry. It activates a relay module to power a water pump if needed. If your system includes a Wi-Fi module, the Arduino could also send that data to a cloud server or a mobile app to notify the user or log activity for analysis. Now, programming with the Arduino is straightforward. We've got an Arduino IDE that allows you to write code using the simplified version of C++. Upload it to the board over USB, and immediately test your setup. A basic sketch typically includes two main functions, setup and loop. Setup runs once to initialize variables and configure pins, while loop runs repeatedly, making decisions based on sensor inputs. So there's a common pattern. In the loop function, you read a sensor value using analog read or digital read. You compare it to the threshold, then you decide whether to activate an actuator using digital write. You might also use libraries to interface with more complex sensors or network devices such as Wi-Fi.h or software serial.h. Now the .h that references a C library. Now those are for the software serial.h is for serial communication. Now communication is essential in IoT, and Arduino supports a variety of protocols. Serial communication is used to send data to a computer for monitoring or logging. So we talked about I2C and SPI, and they're used to communicate with other sensors or devices on the same board. For wireless communication, Wi-Fi modules allow the Arduino to connect to a network and send HTTP requests or push data to MQTT brokers. Bluetooth and Zigbee are also commonly used in wearable and low-power applications. Now, security is a growing concern, and we'll talk about it in the next module, Module 7. And while Arduino is often considered too low-powered for sophisticated cryptographic routines, there's still steps you can take. For example, using encrypted Wi-Fi communication with newer modules like the ESP32. We see that here. That can enhance your data privacy. You can also use authentication tokens or verification codes to restrict access to your IoT devices. So simulation plays a key role in this module. So you can use Wokwi, online Arduino simulator. You can build a test project, deployed physical hardware. Wokwi lets you write Arduino code, connect virtual components like sensors, LEDs, displays, and simulate behavior in real time. It's especially useful for testing logic, debugging, and experimenting with different designs without risking physical components. So I mentioned that you've got a mini project paper. You're going to choose a topic related to Arduino's role in IoT and support it with research. You might explore how Arduino enables low-cost environmental monitoring, how it supports smart home automation, or how it serves as a learning tool for embedded systems. Your paper should explain how the Arduino is used in your chosen context, what components and protocols are involved, and what are the key challenges and advantages. You also need to cite at least 3 sources, or it could be academic papers, books, credible websites, to support your arguments. As you write your paper, think critically about the design decisions involved in Arduino-based systems. What are the limitations in terms of memory, speed? What about connectivity? How can those limitations be addressed? What role does Arduino play compared to more powerful platforms like the Raspberry Pi from Module 5? How does Arduino support scalability in larger IoT deployments? Another good angle to consider is Arduino's impact on STEM education and the maker culture. Many universities, community labs, and K-12 classrooms use Arduino to teach programming. Electronics and systems design. It's a gateway to more complex platforms and a tool for rapid prototyping and innovation. So to wrap things up, the Arduino platform is a powerful and approachable tool for IoT development. It connects the physical world to the digital one by collecting sensor data, making real-time decisions, and triggering actuators. It's supported by a massive community, enriched by a wide ecosystem of sensors and modules, and it can communicate with other devices through various wired and wireless protocols. Through this module in your upcoming paper, you'll develop not only the technical knowledge to build Arduino-based IoT systems, but also the ability to reflect on their broader applications and implementations. Whether you're simulating on Wokwi or working with physical boards, the experience you gain will serve as a foundation for any embedded system that you may pursue to work on in the future. So that's it for Module 6, and we'll shift our focus to a critical aspect of IoT, which is security, as we move into Module 7. So we'll see you in Module 7.